Okay, on to chapter 6. The area under a curve is 1.0, which means this is 0 here, okay? And this way at the end is 1. So you can't have any probability, has to be between 0 and 1, okay? All right? Any C number, any number, just pretend this number C is 2. This would be -2, this would be +2, okay? If it's the same number, negative C or positive C, doesn't matter. To pick a number. It could be a 10 if you want. If the probability of some Z is 0.22 greater than C, then the same probability is true less than negative of the same number, okay? Which means it's 0.56 in between. So if the probability of greater than C, which is right here, is 0.22, and if I take negative C, it's the same number, negative. The probability of less than that same number, negative C, is also 0.22, so that is true. And again, the total area under the curve is 1. Again, same concept as last time, just a slightly different question. If the probability greater than A is 0.25, that means the probability less than negative A is also 0.25, okay? Which means the probability between negative A and positive A is whatever's left over to get to 1. So if I have 0.25 here and 0.25 here, that's 0.5 total. So that means the probability between the two has to be 0.5 to get me to 1 total, because remember, the area under the curve total is 1. Okay, there's 0 and there's 1. Okay, if the probability of some x is less than 5.2 is 0.41, if a probability of less than 5.2 is 0.41, that means greater than is 0.59, because again we have to get to 1. Now just notice, now this is a minor little detail thing that'll come in handy in the future. How did I know to put 0.41 over here, okay, instead of maybe over here, right? Well, because the mean in the middle, the mean goes in the middle. The mean probability, let's just pretend we have test scores, and the test scores, the mean was 70, okay? Just pretend, test scores, because it's easy for everyone to relate to. The probability that I grab a bunch of tests, there's all these test scores, and I added them all up and divided by, however many, to say there's 50 test scores, and I got an average of 70. The probability I select less than the mean, or 70, is 50%, 0.5. And the probability that I grab a random test that's greater than the mean is also 0.5. So if 0.41 is here, this 0.41 is less than 0.5. So that would go on the left side of the mean, because 0.41 is less than 0.5, which means obviously this is greater than 0.5, 0.59 to get to 1. Just a little thing. When you're drawing these little charts, it helps to know what side of this line to put things on. Okay, a problem like this is exactly why you should do what I just told you in the capture before. Put the things where they belong, okay? Normal distribution, mean is 3. Okay, that mean goes right here. Okay, right in the middle. That mean goes right in the middle, which means if I randomly pick a test score that's more than 3, it's a 50-50 chance I randomly grab one that's more than 3, and same 50-50 chance I grab one less than 3, okay? All right, 0.4. If the probability that I grab a test score that's greater than 5 is 0.4, so greater than means here, and I know the entire distance between the mean and the end is 0.5, as I have indicated here, that means that they're between 3 and 5 then must be 0.1, because I need to get to 0.5, because it's 0.5 from the middle to the end. And 0.4 is beyond 5, which means between 3 and 5 must be 0.1, because this total area is 0.5. Okay, if the probability of Z less than B is 0.65, which is the green. Now, why did I put the B on this side? Because the probability less than, or to the left, is 0.65, which is more than 0.5. So B must be over here on the upper side of the mean, okay? All right, so this is 0.65 is the green, which means the greater than B is 0.35. Well, if we know that the probability of greater than B is 0.35, we must also know that the probability less than negative B is that same 0.35. So the answer is true. I think a lot of these are true, but it's important to understand why. If I were you, I would guess true if I wasn't sure, but I wouldn't count on it every time. But a lot of these are true. Well, I spoke too soon. Here's a false one, okay? Since the area under a normal curve within two standard deviations from the mean, so again, here's mean right in the middle, within 2 standard deviations, which means 2 higher goes here and 2 lower goes here. And remember from remember from the empirical rule way back in, I think, chapter 2, 95% fall within 2 standard deviations of the mean. They're saying above the mean is 0.05. Well, the rest of the curve is 0.05, but it's split. 0.025 above 2 standard deviations and 0.025 below 2 standard deviations lower. Above 0.025 is above more than 2 higher, and 0.025 is also less than 2 lower. Okay, so it's that 0.05. It's true the rest of it is 0.05, but it's split. So greater than, if that said 0.025, it would be correct, but 0.05 is not correct. That 0.05 is split between less than and greater than. By the way, if it's a normal distribution, the mean and the median are the same. Okay, in all normal distributions, mean and median are the same. Now we only give you data up to like 3 standard deviations from the mean, like if you go back to chapter 2, but it is possible, very, 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 very unlikely, but it is possible to have something 3 standard deviations higher or lower from the mean, 4 standard deviations higher or lower from the mean. Like an example would be if I sampled a bunch of cars going down my street, and all of the, 80 of them were between 30 and 35 miles an hour, and one car was 79 miles an hour. The mean would still be somewhere in the 30. It wouldn't affect that mean too awful much, but man, that's way more than 4 standard deviations higher. I mean, so it is possible. So never say it's impossible to get something like that. It's just very, very, very unlikely. Remember, okay, let's do 2 things here. Remind you what Z stands for. The Z stands for how many standard deviations is a particular value away from the mean. And second, it is calculated by doing the X value, which is the, whatever we're evaluating, minus the mean divided by the standard deviation. The Z-score could be positive or negative, okay? If that score we're evaluating, let's just say these are test scores, okay? All right. What is the probability if I have all these test scores that the mean is 24 and the standard deviation is 2? How many standard deviations away from the mean is 27 is what they're asking. That's what Z is. How many standard deviations is a particular test score away from the mean, either higher or lower? Since 27 is higher than 24, then we're going to get a positive Z-score. So the score of 27 is 1.5 standard deviations higher than the mean, okay? If it were 21, it would be 21 minus 24. We'd get negative 3/2 or negative 1.5. So the score of 21 is 1.5 standard deviations lower than the mean because the Z-score is negative 1.5, okay? And again, this goes to exactly what I was just talking about. A data value located 1/2 a standard deviation below the mean, okay? So Z is negative 0.5. This data value is 2.3 higher than the mean above, so that has a positive Z value of 2.3. And in the mean, the mean in the middle is a Z of 0. In other words, the mean is no standard deviations away from the mean. Okay, you can do the math too if you ever come up with a problem, but the Z is 0 at the mean. Any score above the mean has a positive value. Any score below the mean has a negative value. Okay, we're not going to do all these because it's the same basic formula, but we'll do 2 of them. The Z-score for X is 13. It's simply, remember the formula is the X value minus the mean divided by the standard deviation. Now, if they give you a Z-score and they're asking for the corresponding X value, this is the formula. Remember, and remember this stands for the standard deviation, this little Greek symbol here. And this stands for the mean, this Greek symbol here. So that's if they give you the Z value, find the X value, there's the formula. So negative 0.6 times 5 plus 17 gives you 14. Okay, this one, it's not asking you who got the better test score. We all know, we could see that Bria had a better test score of 76 than Whitney did at 71. However, what they are asking for is relative to the rest of the people in the class, who had the better score. Well, the answer is whoever had the higher z-score. In other words, how many standard deviations away, who has more standard deviations away from the mean. Okay, if they're both positive, then whichever one's bigger. Okay, if they're both negative, whichever is less negative. So in other words, whoever has the biggest z-value, because that tells you how many standard deviations that score is away from the mean. So if we did Bria's, Bria is 0.2 higher than the mean, so they both did better than the average, okay? But Bria was 0.2 standard deviations higher than the mean, and Whitney's was more than 1 standard deviation higher than the mean. So even though they both did well and they both were above average, Whitney's, in relation to the rest of the class, had a better score, relatively better score than their peers.